Okie dokie. What am I doing? All right. So last time we talked about uh, the singleton design pattern, right? So we've been talking about design patterns. We talked about MSC. MSC is MVC is model view controller. It's the idea that it's a good idea to keep things separate. So your interface is in one place, uh, uh, your code is in another place, your data is in another place. So these are all things that are good ideas, but MVC doesn't mean implementation. So MVC is an idea, and each product will have its own version of that implementation. We've seen how Unity does this by allowing us to have public variables in the code that then exposes it to our project. So similarly, we have another design pattern called the singleton design pattern. Singleton design pattern says it's a good idea to keep information that needs to be shared among many screens, many game objects. Think about how you want, but information that needs to be shared among multiple things, keep it in a single place so that they all have easy access to it. And something I mentioned last time that this is kind of in a little bit in contradiction to from the history of computing. You'll see this in some programming textbooks, is that global variables are bad ideas. And that's one of those things that's probably 97% of the time a true statement, but there's 3% in there where it's the right tool for the job and you might as well use it, just don't abuse it. Same thing's true with singletons. Once you see how easy it is to work with singletons, you then get into the habit just because it works and you maybe don't understand the scoping rules very well. Your cop out might end up being that, oh, I'll just throw everything in a singleton and it's just magically available anywhere I need it. And then you have these singletons with 7,000 variables in them because, hey, it worked. It's true, but I promise as your applications get larger and larger and larger, the fact that it worked is not going to be a good enough excuse because you're going to have a lot of variables. When you start losing variables inside of your singleton, or you have to come up with multiple singletons with like very specialized names, almost like they're folders, like, like these are the variables for these 11 screens to talk to each other or something like that, things start going south pretty quick. All right. So what we were trying to accomplish, let me get some of the code open here. Is we wanted to have our two game objects, player one, player two, count to some number. You can make them stop if you want, or just rely on the update method to bounce back and forth in perpetuity until you stop your game. Doesn't matter. But I want them to alternate on who counts next. All right. So right now what we have, let me open up my singleton as well. All right, so here's my three classes. Now, just as a reminder here, notice that my singleton is not a mono behavior. So player one controller, this thing is meant to attach to a game object. Player two controller is meant to attach to a game object. That's why both of those are mono behaviors. If it's not a mono behavior, you won't be able to attach it as a component of a game object. My singleton is not meant to be attached to game objects. Instead, it's going to be utilized by game objects for communication. Okay. So it's something that's going to exist in the program. It just magically is created and we're filling it with static things. So I don't even need instances of this. We'll be able to make instances of stuff soon enough. And we won't have to do anything special, just the same thing, take mono behavior off of it. But we just have access to the singleton. So inside of update right now, I think what we had at the end of class last time is we had our both our players. Player one would update with his counter. Although right now we took counter away. Player two would also update with his counter. We took counter away. All right. So maybe we put counter or count inside of my singleton. So let's get that working first. And just so we know it's not a default value, I'm going to set count initially to 13. Okay. Actually, what is it? Is it 42? Hitchhiker's Guide to the Galaxy? Answer to everything. We'll make it 42. All right. So I want, at this point, they're not going to be alternating. Because remember, the update method gets called every single frame. So at this point, what I'm going to see is player 1, 42, player 2, 42, player 1, 42, so on and so forth, right? Okay. Now, if we look at our singleton, we see that this guy he's a field because he's a variable, right? He's inside of a class. Classes are made up of three things: fields, constructors, and methods. They come in two flavors, static and non-static. Okay. This guy is static, which means he's owned by the class itself, not an instance of the class. So a static variable count, we would call it using the name of the class in which this variable was defined. So that is my singleton dot count. So inside of our player 1 controller, we would say my singleton dot count. That's how we get access to that variable. Player 2 controller, my singleton dot count. All right, I'm going to go ahead and take these couple of things out here just to get the ball started. All right, so right now count only exists in one place. It exists inside of our singleton. I've set it equal to 42. Neither of my controllers modify it, so it's always going to be 42. But they both reference it. Here, I'm going to get rid of it from the start function here too. So that means every single time this update function gets called on any game object that has a mono behavior, which for this case, these two game objects, their update method both talk about my singleton.count. So we're going to keep printing 42 to the screen over and over and over and over again. Command Shift S, right? That's weird. All right, so I have them saved. So now we'll come back to our game here. I'll switch over to our console. We'll hit play. We see down here, it's always 42. And they're just printing it whenever they happen to have their update method called. Now, we do notice, and I think we talked about this last time, that they actually are alternating right now. And this is because of the way behind the scenes that update methods get called. They seem to be loaded onto a stack in the order in which we put the game objects into the scene. And all that game objects components get accessed or get called for the update method once per frame. And it just so happens that printing a single integer isn't enough of a burden for there to be a delay in our things printing. All right, so it is still alternating back and forth, where if we did have in one of our update methods something that took too long, it might actually create a hiccup where player 1 puts two things in a row or something like that, because we're relying on when that update method gets called to make our next decision. Make some sense? All right, so that means it would be unwise for us to rely on how update is getting called in order to do this alternating. So we're gonna have to come up with our own little mechanism for controlling who counts when. All right, so maybe we come into the singleton here and we do something like public static bool player 1 turn. Start that off at true. So we'll create a variable of type Boolean, which holds trues or falses. And we will start it off at true. Whenever player 1 turn is true, then player 1 will show the count and increment it, and then flip the player 1 turn to false. So that the next time through, we'll say player 2 only prints and increments the count when it's not player one's turn. When it is player one's turn, he displays stuff. When it's not player one's turn, player two displays stuff. All right, we'll start our count off at 0 here. We'll go into player one. We want to have an if statement here. Player one is only going to do anything if my singleton dot player one turn. That's good enough, because if we say is equal to true, is true equal to true, that's true. So it's actually redundant to say equal true, but I'll keep it in there for right now so it drives this point home that we're saying whatever this value is, if that value is equivalent to true, then player one is going to do something. And when it's player one's turn, what is he going to do? He's going to display the count. He's going to increment the count. And then he's going to flip whose turn it is. Make sense? Steal the beginning of that there. So that's for player one. Player one, when he notices its turn, his turn from the singleton, when his update method gets called, he looks up at the singleton and says, is it my turn? It is. Display, increment, other guy's turn. All right. And after that's done, we'll go ahead and see this. I'm going to actually comment out. So right now, player two won't do anything. So the very first time through, we have our singleton, count 0. We turn is true. So when player one comes through here, he'll say, is it my turn? Yes, it is, because player one, it is your turn. Okay, I'll go ahead and print out the current value of my singleton dot count, which is going to be a 0. Then I'll increment it to a 1. Then I'll say it's no longer my turn. And at this point, there's nothing else in our code that ever flips it back. So every single time through player one's update method, he's going to ask that question. Is it my turn? Is it my turn? Is it my turn? Is it my turn? And every single time except the very first time, he's going to be disappointed. Okay, so he's never going to get to say anything again. Let me make sure everything's saved. Right. So we'll go ahead and run this guy again. So there's my player one, 0. Okay. And he only did it one time. All right. He's still checking, right? Every single frame, he's still asking that question. As we speak, he's still asking that question. But he's never actually putting something else out there. So now we'll go into player two. I'll steal the first part of this. So if it's not player one's turn, if I'm player two and it's not player one's turn, what am I going to do? I'm going to print out the current value of count. Then I'll increment count. And then I'll flip it back to player one's turn. All right. So player two only does something when it's not player one's turn. Player one only does something when it is player one's turn. And in both of those cases, they flip it to the other guy's turn at the end. All right. So now when we run this, we should get it counting back and forth. Blah, blah, blah. What'd you do? All right, so we see it counting back and forth here, alternating. So this is one way you could have, I'm going to say mostly have pulled this off. They're actually, oh, and by the way, this class attribute thing, it must be a new thing in Unity. There's probably a macro thing I have to put on the top to say I purposely am making this not a mono behavior. It's just a warning, so you can just ignore it for right now. It's missing the class attribute extension of native class. So there's something I'm supposed to put at the top of those files to preheat it that I did that on purpose. All right. So right now this appears to be working. Now I'm going to tell you there is a potential problem here. Go back to the code. What could the possible problem be? And we're not going to really come up with a great solution to it in here because it's really more of an operating systems level problem, but it's something for you to maybe be aware of and think about for the future. So right now we have two different scripts competing for who gets to announce the next count and change the count, right? They're doing two things each time through. And if we think about them like a bouncer at the door, we have this one Boolean variable, right? That one Boolean variable, the player one turn, right? My singleton dot player one turn, that is effectively the bouncer that's standing at the door that decides whether he's going to let somebody in or not let them in, right? All right. So with that in mind, there is a potential possibility. I guess it's possible that Unity has protections built into it against this, but let's assume it doesn't for lesson's sake. We have something in computing known as a race condition. So that would be a situation where, let's say, two people are trying to get into the club and they both arrive at the bouncer at the exact same time. And however the bouncer authenticates them relies on being able to deal with one person at a time. And since they both got there at the same time, they're either both turned away or both let in erroneously, something like that. And it's because we have the ability to look at that both player one and player two can both look at my singleton dot player one turn at the same time. They can both interact with that at the same time, potentially. We have no way of guarding that. All right. So there are mechanisms in operating systems. It's related to interprocess communication. Actually, the thing we talked about at the end of last semester and beginning of this semester with threads. When we have more than one thread that's talking to each other, you know, if they're sharing information between the two of them and they're reliant on having that information be done before we move forward. We saw with our threads, we use the wait. Actually, no, we use the join function, right? A thread joined another thread, and that said, okay, I'm going to wait till he's done. That was our way of blocking him from going and doing any additional checking using elements in our array before they were sorted, that kind of stuff. So it's a way of putting a mechanism in there to protect a resource until it's ready. Okay. We have several different approaches to that at the operating system level, where we attempt to make access to something what's called atomic. It means it happens in exactly one instruction. Now, realistically, one instruction on the CPU, that is, which, you know, a computer can only do one thing at a time per CPU. But now we have multi-core CPUs, so now we got to protect across multiple CPU instances. So let's not even go down that path. Just know it makes the problem harder. But we do have mechanisms built into operating systems that allow us to effectively create a section of code that's called the critical section that effectively locks down. So it says, I'm the only one who has access to these 3 lines right now. And so since I'm the only one who has access to this, anything I do cannot be undone by somebody else until I relinquish control of this thing. In Unity, I'm guessing it's probably synchronized. Would be our easiest way to accomplish it. It's this lock thing. That's one way of doing it. We can lock down a piece of code. Like I said, we're not going to dive into it too much, but there are mechanisms built into Unity that allow us to do this. Most of the time, it's not really going to be a problem, especially not in a situation like this where what's the worst that happens? They count out of order or something, or they both spit out the same number at the same time. We don't call off a rocket launch or something like that because of that in this case. So we do also have to consider how important it is, the data we're working with. But just know that there is the existence of something called a race condition when we've created a scenario here where two players are fighting over a variable, and both of them are changing that variable. In this case, they're changing two different variables, right? Because just because if they get into the club, if we assume this is the bouncer, once they're in the club here, they're not only changing that Boolean variable, they're also changing our counter. So if we imagine, well, this might take, let's say 7 instructions at the CPU level. And let's say this takes 4 instructions at the CPU level. That means there are 11 instructions that are occurring in there, even if we ignore the IO, which I've already told you is slow, right? So IO is already stalling things. But even if we just look at those 2 lines that feel like they should be super fast, there are 11 individual instructions that we are telling the CPU to do, where somebody else might find a time to jump in the middle, and maybe count gets incremented 2 separate times before the next guy prints or something like that. Those kinds of things. You can get some weird behaviors, and that's around this thing called a race condition. It's operating system concept. You're only going to have to deal with it in game programming in very, very important things. And usually when you get to that point, it'll be something with network programming, and that'll make sense to you. So I'm not going to dive down that path too much. Just maybe make a note that this could be a thing. All right. So I think that gives us a reasonable solution to the homework. Are there any questions on that? If we ultimately wanted to stop at 5,000 or something like that, we would just enhance our if statements. If it's my turn and it's not greater than 5,000, let's do some stuff. Something like that. And then he would stop spitting stuff out, yet he's still asking the question every single time through. Now, this might be one of those situations where we do decide that perhaps fixed update is good enough. So if I change my update here to fixed update, and I'll do it in both of these. And then we run it. We see that actually one thing you should see there is, doesn't it feel like it's going a little slower? Feels a little bit more controlled than we saw before? Because before we were already up in the thousands, right? Remember, what's the difference between update and fixed update? But
Fixed update is locked at 60 frames.
Yeah, locked at 60 frames a second. So that means that we're only calling that function every 60th of a second, as opposed to every single time a frame can be displayed by this graphics card in this computer. So we might decide something like this. Actually, we have a couple of different things going on here. By moving it to fixed update, we probably have reduced the possibility of a race condition. Similarly, by our observations in the past of it, the order in which it's calling those update methods, where it seems like it's never calling two game objects update methods at the same time. It calls them in a linear order. Seemed like in a reverse order to when we added them to the scene. It seems like a race condition is also actually protected in this case because of that. We don't move on to the next game objects update method until the current game objects update method has completed. Therefore, we're actually accidentally protecting this race condition just by the way update gets called. Good programming practice would probably say don't rely on something like that. Because you never know when the next update to Unity comes out and they decide, hey, we can streamline our games by calling update methods in parallel or something like that. And it's possible they already do that and we're just not seeing it because we don't have enough game objects or something. But, maybe once maybe for every 10 game objects, they add another thread for calling the update method on those or something like that. So just imagine that idea where you probably wouldn't want to rely on the way this game engine currently works to make your logical decisions on when it might be an important piece of data, updating a database or something like that. If somebody changes their password and two people are changing it at the same password at the same time, which one sticks, whichever one saved last, that's your new password. Probably want to protect that. Don't allow the same password to change at the same time because somebody's going to not know what the password is at that point. Hopefully it's the person who actually owns the password. Well, hopefully it's the one who was trying to steal the password, not the one who owns the password. But hopefully you get my point. So don't rely on default behaviors of things. If you want something to be protected, write your own code to protect it. Okay, questions about any of that stuff? All right, so let's start working on let's start bringing some of our stuff in from our dungeon crawler, but we're going to start off focusing on these players since that's what we have in the scene right now. So we want to create a player class. Let me open up Keynote here. All right, so in our player class, we're going to say all players have a name and maybe have a number of hit points. Keep it reasonably simple at first. Okay, so we're going to write a class for player. Now, this guy is meant to be a data structure. So we want this guy to keep track of information about a player, but he's not something we're going to hang on our player. So this comes down to that decision making. Is this a mono behavior or is this not a mono behavior? So as I mentioned last time, you can add it to the project here, but what I almost always do, let's call it possibly just out of habit, is we create a folder last time called normal classes. I'm going to create a C# script in here. I'm going to call this guy player. So I want you to think about this kind of like our player class that we wrote last term. We had players and rooms and that kind of stuff. All right, so we have our player there. I'm going to go ahead and open that. So now it's open in here. The very first thing I'm going to do, I'm going to say, you're no longer a mono behavior. Because I'm not going to be hanging you off a game object. Instead, I'm going to have game objects create instances of you. And you're going to see that here in a second. So I'll go ahead and gut my mono behavior stuff from this. And now we want to think about this guy as being a plain Jane class. Just like in Java, just like in C++, we're just happening to write it in C# right now. So we're going to have a private string name. And we're going to have a private int hit points. All right. So we'll go ahead and write our constructor for this guy. So we're going to say when we build a player, we're going to give him, well, we'll provide the name. We're going to say your name is Mike, your name is Dave, you know, whatever. And then we're going to randomly set the hit points to something. So we'll have to go and look at, we randomly do stuff in C#. C# random int. Oh, look at that. It's pretty much the same thing as we have in Java. All right, so I'm going to create a random r is equal to new random. And this guy must live in a different class. Oh, it's actually looking at Unity's random. That's fine. We'll use Unity's instead of C#'s built-in random. So we have a thing called, I think, random.range. Here we go. Random.range, and you just give it the smallest and biggest value. So this is part of Unity. If I click on that, here's random.range. It's one of the classes built into Unity. So we'll use that guy. As you might imagine, video games, you do a lot of random number stuff. So I'm going to kind of sort of trust that maybe their random number generator is more gamey centric than the generic C# random number generator. What's it called? Random dot range. So we're going to say int. Well, we'll say this dot HP is equal to random dot range. And this guy, he returns a float. So it's a minimum inclusive value and maximum inclusive value. I actually like that in the documentation. I don't know if it's big enough on the screen for you to see there. But one issue you run into with random number generators, I would say fairly often, is you're kind of wondering, well, if I say 0 to 10, is that giving me 0 to 10 including 0 and including 10? Or is it giving me a 0 including 0, but only up to 9, so it's not including 10, so on and so. That's pretty common, those two options. I don't know if I've ever seen one where it doesn't include the first number, but it is common to question whether or not the bigger number is inclusive or non-inclusive. So I'm making the assumption, but this is a good example here of having variables that have meaningful names. The parameters that are coming into random.range are a float called min inclusive and a float called max inclusive. So I kind of like that because it's the variable name is letting me know this is inclusive. So I'm going to say we're going to have a hit point range of, we're going to say 10.0F. I'll talk about that here in a second. And maybe 20.0F. Okay. And if we look at the documentation here, we see this guy actually returns a float. I want to put it inside of my hit points. So I'm just going to say, whatever you give me, just make it an int. Typecast it to an int. So when you typecast a floating point value to an integer, you're not rounding at all. All you're doing is cutting off the decimal point. So 10.01 is a 10, 10.99 is also a 10. Okay. So I set my hit points to some random value, and then I'm going to go ahead and set my name to whatever was passed in. So this dot name is equal to the name that was passed in. All right. And then for right now, we're going to give ourselves a public void display function where a player gets to display themselves. So we're going to say I'm in a different namespace here. So what was it? Debug.log. Yeah, debug.log is the C# version of this. So I'm going to say this dot name concatenated with, maybe we'll put an arrow and we'll say HP : and then this dot HP. All right, so the display function here for our player, which will go out to the console. All right, so this is similar to what we might do to debug in a C++ or a Java program. Shortly, we're going to be putting little little signs over our player's head with their name on it and their hit points, that kind of stuff. But this will at least show us that we can make this work. All right, so what does a player do? A player lets us create a player with a name. It gives us a random number of hit points between 10 and 20, and then we have the ability to display. So what we're going to do inside of our controllers here, I'm going to go ahead and I'll just comment out this code since we don't really need them counting at the moment. And what I'm going to do is I'm going to have and you saw this kind of in the original tutorial that you did. I think you had a rigid body up here that you had access to other places. So I'm going to have a private player. Call this guy the player. And then inside of start, remember this guy only gets called once. So we kind of think about this as like our constructor for this guy. We're going to say this dot the player is equal to a new player. And this is going to be Mike. Right. And I'm going to steal that for our other controller. We'll call this guy Dave. All right. And then for both of these guys, we look at our player class. We see that here's our function called display. Is that a class method or an instance method? How do you know? We're looking at our own documentation. No static. So that means it's an instance method. How do we call instance methods? What do we need to call an instance method? Emphasis being on the word instance. Strong emphasis on the word instance. So we call instance methods using an instance of the class in which the method was defined. We call class methods or static methods using the name of the class in which the member was defined. So in our singleton, notice that these fields are all static. That's why we called them by saying my singleton.count, my singleton.player1turn. All right, these guys were they only exist one time and they're owned by the class called my singleton. Where in this case, all the stuff in here is non-static, which means every single instance of player, if we create 1,000 instances of player, they each have their own name, their own hit points, so on and so forth, their own display function. So what we'll do here inside of our controllers is we're going to say this dot the player dot display. So fixed update inside of player one controller will tell his player to display himself every single time. So we'll get a lot of outputs. And we're going to do the same thing here in this guy. So just proving that we did create instances of players with the differing names and see what their random hit points are. And we should see that they get different numbers of hit points each time. I'll hit play here. All right, so there's Mike with 13 hit points, Dave with 17 hit points. They're just printing it over and over again. I'll go ahead and run this again. And we got 18 and 10 for hit points this time. So it's random stuff. All right. So right here at the end of the video, I'll show you our two classes. I'll try to also give them to you up on Slack or with the assignment or whatever. So here's our singletons. Here's our player. All right. So based on what you learned from the tutorial for your homework for Wednesday, make the name and the hit points of each player float around the player in the scene. So in our scene right now, we have no way of controlling our guys, but I want to see maybe Mike and 10 above this dude and Dave and 17 above this dude, whatever the hit points are for them. Make sense what I'm asking to do? Because eventually, when we have our video game and we have these guys fighting to the death, we want to be able to see the hit points going down, right? And then maybe we do some particle effects that instead of blood, we'll do confetti or something. You know, we don't get it too violent, but all right. Questions, comments, concerns, bribes. Bribes. All right, I'll see everybody on Wednesday.